Well, good afternoon, everybody, and welcome to this session. My name is David Bogle. I'm to chair this session, and I'm here to introduce this Danckwerts lecture as one of the Chemical Engineering Science executive editors, and also as the scientific vice president of the European Federation of Chemical Engineers. So it's my great pleasure to introduce this, the 2021 Danckwerts lecture, on behalf of the editor-in-chief of Chemical Engineering Science, Professor Anton Middelberg, who's in Australia. So just a few words about the Danckwerts lecture before I introduce the speaker. This lecture was set up by the publisher of Chemical Engineering Science. It was then Perkins Press, and it's now part of Elsevier, together with the UK Institution of Chemical Engineers, to honour Professor Peter Danckwerts. And the first lecture was given in 1986 by Professor Neil Amundsen. So a little bit about Danckwerts. Following a very distinguished war career, where he was awarded the George Cross for disarming landmines, Danckwerts, who was an Oxford graduate, was awarded a Harkness Fellowship to undertake a master's degree in chemical engineering at MIT. There followed a career at the UK Atomic Energy Authority, then at Imperial College London, but principally at the University of Cambridge, where he was Shell Professor from 1959 to 1977. He was Editor-in-Chief of Chemical Engineering Science, also from 1976 to 1982, and passed away in 1984. His research interests were very broad, but particularly focused on gas-liquid reaction systems, and perhaps he's best known for his theory of residence time distribution in chemical reactors. But his interactions throughout his career, his interactions with industry, were very strong. So this Danckwerts lecture is held annually, and it's co-sponsored by Chemical Engineering Science, the Institution of Chemical Engineers, the American Institute of Chemical Engineers, and the European Federation of Chemical Engineers, and is held in alternating years at the ECCE conference, that is this year, and at the EECE meetings. So this year's Danckwerts lecture will be given by Professor Michael Doherty. Mike Doherty is the Duncan and Susan Mellichamp Chair in Process Systems Engineering and former Chemical Engineering Department Chair at the University of California, Santa Barbara. He's a member of the US National Academy of Engineering. And a bit about his history: he received his Bachelor of BSc in Chemical Engineering from Imperial College London, and his PhD in Chemical Engineering from Trinity College, University of Cambridge. And he and I had, as it happens, the same PhD supervisor. So on the Sargent family tree, we are considered as brothers. Among too many awards to mention, to mark its centenary in 2008, the AICHE named him one of the 100 chemical engineers of the modern era, post-1945. So the award committee felt that Mike would be particularly fitting lecturer, given the way that he spanned the links between industry and academia in his career in a way similar to Danckwerts. He served as a consultant and expert witness for many companies in the area of separations technology, and is currently a member of the scientific advisory boards for Royal Dutch Shell Group, and has been in the past for Dow Chemical Company, Roan Poulenc, and several smaller companies. So Mike's lecture is entitled Practice and Science in Continuous Manufacturing of Pharmaceuticals. So welcome, Mike Doherty, for this Danckwerts lecture.
Thank you, David. I should say Brother David, for that warm introduction. Let me begin by thanking Anton Middelberg and the selection committee for allowing me to give this lecture today, and for trusting that I'm not going to mess it up. Although I've spent my entire professional career in the United States, and today I'm speaking to you from California, I have to say I do feel quite at home with this European audience, because, as David mentioned, I was born and educated in Europe. I've maintained close relations with many European scientists and engineers throughout my career. And I would especially like to mention, in that regard, Stefan Wiesler in Marseille, Marco Mazzotti in Zurich, Roger Davey in Manchester, Andreas Seidel-Morgenstern and his colleagues at the Max Planck Institute in Magdeburg, and most recently Sally Price and Matteo Salvalaglio at University College London. I've chosen to speak today about pharmaceutical manufacturing in recognition of the wonder drugs that have really improved the quality of our lives, drugs such as penicillin, insulin, and the many drugs that are used to treat cancer, HIV, schizophrenia, and many other ailments. Also because the second half of my career, for the last 25 years approximately, I've spent that time in crystal engineering, studying crystal engineering, publishing on that topic. So it's a topic I feel well qualified to speak about. Let me share an outline of my lecture. I want to begin with some personal reflections on Peter Danckwerts, who I knew personally. I then want to spend about 35 minutes talking about the technical subject area. And I'm going to finish with some personal reflections on my PhD supervisor and David's, John Perkins. So, as David said, I went up to Cambridge in 1973 after graduating from Imperial College, and I joined the department that Peter Danckwerts was the head of. He was the Shell professor and head of department at that time and remained so throughout the period where I was a student. He was clearly the man in charge. He was quite austere, reserved. At least that's the way we students thought about him. And this photograph is how I remember him. But in spite of his personal reservedness, he must have actually had a warm heart, because at the end of our first year, each of us had to write a report to him, which he read and wrote notes on. And then each of us had to go and have a 1-hour oral examination from him alone in his office. And in spite of all the drivel that he must have heard from us all, he passed almost all of us and allowed us to go on to continue with our PhDs. His right-hand woman was Margaret Sansom. She spent her entire career in the department as the executive assistant to the head. And she was really the organizational brain behind the department. When you went to her office, her authority transmitted the unspoken words. Do you want to speak to the man in charge or to the woman who knows what's going on? In person, Danckwerts did not seem to have a very high sense of humor, but he actually did have a very nice sense of humor, and this comes out mainly through his writings. And I've chosen to demonstrate this with a review that he wrote in 1982 of the book A Century of Chemical Engineering. His review begins with the sentence, "The surprising thing about this book is that it's a lot less boring than it sounds." Later in the review, he states, "I was amused to find that the treatment of the tubular reactor with longitudinal dispersion, together with the Danckwerts boundary conditions, which I put forward in 1953, and which were credited to me for at least 25 years, had been anticipated by Langmuir in 1908. He goes on to write, I should have been less amused in 1954. Danckwerts lived in the center of Cambridge in a really beautiful medieval house that was a former abbey with large, spacious grounds. And each summer, he would have a garden party for the PhD students in the program. As you can see, there weren't very many of us. There's a few more off camera, but nevertheless, the total number of students in the department at that time was perhaps 20 or 25. And here is a younger and slimmer me talking to Peter Danckwerts at one of those garden parties. And off to the left here is my classmate, Tom Conley, who spent 10 years of his career as Chief Technology Officer at DuPont and is currently serving as the Chief Executive Officer of the American Chemical Society. Although Peter Danckwerts was nominally the host of these gatherings, it was actually his wife, Lavinia, who made us all feel quite comfortable and relaxed, and no doubt that was also aided by a glass or two of champagne. In addition to Lavinia here, I'm showing an image of my wife, Margaret Ricks, who also used to attend these parties with me. Danckwerts had many outstanding students, and I'd like to pick on two who I've known personally. One is Professor M Sharma from the UDCT, Bombay, University Department of Chemical Technology, now known as the Institute of Chemical Technology, Mumbai. Sharma is truly an outstanding chemical engineer, certainly the best in India, and one of the very best worldwide. He was the director of that institute for around 25 years, and he was the man that really turned that institute into the world-class institution that it is today. I'd like to also mention Sir Max Richards. Max Richards was a contemporary of Sharma at Cambridge, also working for Danckwerts. He began life working as an engineer at Shell in Trinidad, who quickly recognized his talents and sponsored him to go to the University of Manchester to study for a bachelor's degree, and then to Cambridge to study with Peter Danckwerts. After he graduated, he returned to Trinidad and Tobago as a professor of chemical engineering at the University of the West Indies, and subsequently became president of Trinidad and Tobago for 10 years between 2003 and 2013. So after those personal reflections, let me move on and talk about the digital design of drug products and processes. And let's start with a view of a medieval alchemist's manufacturing laboratory. Humans, for millennia, have made lotions and potions, poisons and medicines, and it's medicines that I want to talk about today. In the Middle Ages, they were made in a laboratory that looked something like this. Of course, today, they're made in manufacturing facilities that look more like this. So how did we get from there to there? Well, we know the answer to that. Centuries of scientific achievement where we discovered the laws of conservation of mass and energy, momentum and charge. We discovered the laws of thermodynamics. We developed rate models. And in the last 50 or 60 years, the great developments in process systems engineering, particularly in the area of simulation. Much of the work in simulation has been focused on fluid systems, covering fluid phase reactors, distillations, liquid extractions, and so forth. And one of the challenges for the future is to develop those same methods for particulate processes, and particularly for pharmaceutical manufacturing. So over the last decade or so, most people who work in this space have come to embrace a workflow that we typically call something like digital design of drug products and processes. And the workflow goes something like this. The medicinal chemists identify a target molecule. These molecules typically are fairly high molecular weight, perhaps 400 or 500, so that under ambient conditions they are solids, crystalline solids typically, not liquids or gases. So we have to manufacture these drugs as solid products. And so the first thing that is undertaken, typically, is a crystal structure prediction and exploration, where the various polymorphs, the various crystal structures that these drugs can crystallize into, is determined. And one of those structures is typically selected to be the product, which is registered and patented and so forth. Once the polymorph is selected, we need to know its solubility in a variety of solvents and also its nucleation and growth rates in those solvents. We then need to develop a manufacturing process that will produce the polymorph that we've chosen, perhaps this one, not the bottom one. I don't know whether you can see my pointer. This one, perhaps, rather than that one. At the same time, we'd like to know something ab initio about the shape and the morphology of the crystal. Crystals grow into all manner of different shapes, rods like I'm showing here, hexagonal plates like I'm showing here, more equant shapes like here, or thin, long needles, which are typically not desired. And so it's good to be able to estimate in advance what the morphology of the crystal will be in any particular solvent. And then finally, all of this is assembled into a manufacturing process where we determine, for instance, the size distribution, the mean particle size, and so forth of the particles that we make. So let's begin with a more formal definition of what I mean by polymorphism. It's the ability of a solid to take on more than one crystal structure and yet lead to identical liquid and vapor states. Different polymorphs have completely different properties. They have different crystal shapes, they have different growth rates, they have different colors, different mechanical properties, electrical properties, and in particular for pharmaceutical manufacturing, different solubility in the same solvent and different dissolution rate. If a crystal takes 12 hours to dissolve in the body, for example, that particular polymorph would not be an effective drug. The first time that I know of that polymorphism was described in the literature was a letter that Michael Faraday wrote from Italy in 1814 to one of his colleagues in England. At that time, Humphrey Davy and Michael Faraday were on a scientific tour of Europe, and one of the countries they visited was Italy. And they visited the Duke of Tuscany, who had an enormous telescope on his property. And what Davy and Faraday did was they turned the telescope so that it focused the sun's rays onto a stone tablet, onto a stone table, and at the focal point they put a diamond. They used the telescope, the inverted telescope, to bring intense heat on the diamond, such intense heat the diamond actually vaporized and reacted with oxygen in the air. They collected the oxygen and determined it was carbon dioxide, which made Michael Faraday write the following. In this experiment was repeated several times, and in all cases the same striking phenomenon was observed, a phenomenon which lessens considerably the difference existing between diamond and charcoal. So in the first step of this workflow, the typical thing that one does is set up a simulation of all of the atoms in all of the molecules in the crystal lattice. And then move all of those atoms so as to get different configurations of the molecules in the lattice. And for each configuration, for each, as you vary all of those degrees of freedom, you have a highly sophisticated quantum mechanical electronic structure calculation that determines the lattice energy of that particular configuration. You then search for minima in the lattice energy, and each of those minima are thought to correspond to potential polymorphs in the landscape. And I'm showing here a plot. This is the way we typically plot these things, of lattice energy on the ordinate axis against the crystal density on the abscissa axis. And I'm showing a plot here for succinic acid, in which the two common forms of experimentally observed forms, I should say, of succinic acid, the alpha form and the beta form, are shown along with a collection of other potential forms. But it was calculations of this nature that gave Sally Price at UCL and her colleagues the indication that there might be another form that could be experimentally observed. They then, with their collaborators, went into the laboratory and discovered the gamma form, a new form. And so these crystal structure calculations can give very helpful insight into which forms are likely to be observed experimentally, and can even give hints about how to find them experimentally. So this particular study was performed by Sally Price with her colleague Matteo Salvalaglio, using software developed at Imperial College by Claire Adjaman and Kostas Pantelides. Once the crystal structure landscape is understood, the next thing we would like to know is the solubility of the chosen polymorph or polymorphs in a variety of solvents. And that now can be performed by molecular simulation. It's only in the last 5 or 6 years that this has become possible. And so the way one does that is one makes a plot of the chemical potential as a function of the solute composition. And for the solution, one calculates the chemical potential as a function of the solute composition in solution, and you get a curve that looks like this. And then one plots the chemical potential of the pure solute, which is horizontal. And where these two curves intersect is the saturation concentration, or the solubility, of the crystal in that particular solvent. One can repeat this calculation at various temperatures and even at various pressures if desired, and make a Van 't Hoff plot of the logarithm of the saturation mole fraction as a function of the reciprocal temperature. And typically one finds that these plots are linear, even though the molecular simulations have no clue that they're supposed to do this. One finds typically that the plots are quite linear, which allows for easy interpolation of the data or of the predictions, and even a little bit of extrapolation if one is daring enough to do that. This kind of calculation has now been performed for a variety of crystals in a variety of solvents. Some of them I'm listing here. And over the last 5 or 6 years, the pioneers of this field are Carlos Vega in Madrid, Dan Frankel at Cambridge, and Thenos Panengiotopoulos at Princeton. So now let me turn to polymorph selection. As I mentioned earlier, polymorphs come in many different crystal forms and crystal shapes. And I'm showing here some data for glutamic acid. There are 2 polymorphs of glutamic acid, the alpha form, which is metastable. This is the alpha form. And the beta form, which is the most thermodynamically stable form. If one plots the solubility of each of these forms in a given solvent as a function of temperature, one typically gets plots that look like this. If one starts with a supersaturated solution, crystals will nucleate and grow and drop out of solution, and as a result, the solution desupersaturates and the concentration of the solute in solution decreases. So we follow at constant temperature a path that looks like this. The concentration drops to the point where eventually it gets to the solubility of the metastable form here, but keeps on dropping because the beta form keeps on nucleating and growing. And so once we get to a point like here, the alpha crystals recognize that they're undersaturated relative to their saturation curve, and they start to dissolve. Meanwhile, the beta form keeps growing until eventually we get to this point where we have thermodynamic equilibrium between the beta form and the solution. You'll notice from this argument that the thermodynamically most stable polymorph must always be the least soluble. That's a golden rule in crystallization, that the most thermodynamically stable polymorph is always the least stable. Now you can see the problem with this. If that least stable polymorph, if that least soluble polymorph has very low solubility in water, for example, water being a proxy for the fluids in the body, then it might well be that a metastable form is the desired form to produce for a drug in a manufacturing process in order to achieve the increased solubility in the body. Batch processing almost always gives the most stable form as the product. And so a continuing problem in manufacturing solids is how to get metastable forms on demand in a process. And one of my former PhD students, Thomas Farmer, took a crack at this, and he decided there is probably a chemical engineering solution to this, namely, let's see what we can develop through a continuous process. So the concept is we feed a supersaturated solution into a continuous, well-mixed crystallizer. We take continuously a slurry of the crystals formed and the desupersaturated solution in the exit stream. And so we set up a steady-state model for a crystallizer of this sort for each of the two polymorphs, let's say the alpha polymorph and the beta polymorph. You put together a pair of coupled population balances to do that, and they are augmented by the solubility relation for each of those polymorphs in the given solvent, as well as nucleation laws and growth rate laws for each of the two crystal forms. Then you can put the model into dimensionless form, which in turn produces the relevant dimensionless groups, which become the parameters in the model. There are 4 parameters the designer can vary. The inlet supersaturation is something that we can manipulate. The temperature inside the crystallizer, the residence time of the crystallizer, and of course the solvent. We can pick the solvent. When Thomas performed this study, the first thing he did, like any competent chemical engineer, was determine how many steady states does this model have. Turns out the answer is 3. One steady state is the trivial steady state where no crystals are formed. The second steady state is the beta polymorph, where only beta crystals emerge from the crystallizer at steady state. And the third steady state is the alpha form. He then performed a linear stability analysis, and this is where Thomas's perseverance and cleverness came in. It's a very complicated model, but he was able to plow through the algebra and get analytical conditions for the existence and stability of each of these steady states, and was able to determine from among the dimensionless groups that appear in the model, only one matters. And that is a parameter that we call the Damkohler number. It's actually not a conventional Damkohler number. It's more like a modified Damkohler number, which is a ratio of the characteristic residence time in the crystallizer to characteristic divided by characteristic nucleation time and growth time. And on the plot of the Damkohler number for the beta crystals versus the Damkohler number for the alpha crystals, he was able to determine that at low Damkohler numbers, lower than unity, no crystals are formed. That makes sense. When the residence time is so low, the solution, the supersaturated solution, comes into the crystallizer and leaves so quickly that there isn't sufficient time for the crystals to nucleate and grow. So there's an area down in this region of the diagram where no crystals are formed. If the characteristic growth and nucleation times are small for the beta phase relative to the alpha phase, that puts us in the yellow region. And if your design is in the yellow region, you will get pure beta crystals as the dynamically stable output from the crystallizer. However, if the reverse is true, then the alpha crystals will be the dynamically stable output from the crystallizer, in spite of the fact that they are thermodynamically metastable. So this was a somewhat unexpected result that he found. In order to test this result, he went to the literature and found a series of experimental results from Alan Myerson's group that had characterized the outlet from a continuous crystallizer in terms of which polymorph it was producing. And lo and behold, for each of the approximately 14 experiments that Thomas was able to find, in every case, the experimentally observed polymorph was in precise agreement with what the model predicted. We tested the model further by, for instance, increasing the residence time in the crystallizer. As you increase the residence time, you expect the crystallizer to behave more and more like a batch crystallizer. And sure enough, as you increase the residence time, a path like this is followed, initially giving the metastable polymorph, but at large residence times, the most stable, the thermodynamically most stable polymorph becomes the polymorph that emerges from the crystallizer. So that's a good check. But perhaps the most interesting study was increasing the supersaturation of the feed to the crystallizer, C0, from, for instance, 20 grams per kilogram of solvent to 40 grams to 60 grams. Turns out that follows a straight line path, and the slope of that straight line is less than unity, which means no matter where you start from in this design space, as you increase the inlet concentration to the crystallizer, you will always end up in the metastable region. Now, there are bounds on this. You can't just put unlimited amounts of solute in the feed to the crystallizer. So it may be you start here and can't get all the way to here. But in principle, increasing the concentration of solute in the feed to the crystallizer is a viable path to obtaining the metastable form as the output from the crystallizer. And so we've developed design rules for obtaining these metastable forms. One is it's favored by high feed supersaturation, and the other is it's favored by low residence times, or some combination of the two. So then we wanted to test this ourselves in our own laboratory, and we did. We built a continuous crystallizer in my lab, and we selected calcium carbonate as the target molecule for a variety of reasons, one of which is that calcium carbonate has 3 crystalline polymorphs: calcite, which is thermodynamically the most stable, and that's limestone; aragonite, which is the next most stable; and vadarite, which is really very metastable, quite unstable relative to the other two. In all of the experiments we performed, we never saw aragonite at the temperatures that we were operating our crystallizers at. We only ever observed calcite and vadarite, and they're quite distinguishable visually because calcite grows as cubic crystals and vadarite grows as spheres. So another one of my students, in collaboration with Thomas Farmer, myself, and my colleague, Brad Schmelke, Sina Scheibel, performed a great many experiments in the lab. I'm just going to show you one particularly telling experiment here, in which she plots the percentage of the polymorph, the percentage vadarite and the percentage calcite, in the outlet solids as a function of the inlet supersaturation to the crystallizer, all at constant temperature and all at constant residence time. Her very first experiment was the green point here, which is about 25% calcite and 75% vadarite. We were able to determine this both visually, as you can see here, calcite crystals, vadarite crystals, but quantitatively, we did it by X-ray crystallography and solid-state nuclear magnetic resonance. That's where Brad Schmelke comes in. He's an expert in solid-state NMR. And then Sina varied the inlet concentration from small values, which favored calcite, to larger values, which favored vadarite. And once you get beyond a certain inlet concentration, the outlet solids are essentially 100% vadarite, 0% calcite, and you can see that here in this micrograph. And you can run this continuous crystallizer day and night. We did for days and days on end, and it just locks in on the polymorph that you've designed for and stays there as a dynamically stable state, even though the polymorph is a thermodynamically unstable or metastable phase. So we've developed these rational design rules for polymorphism, or for getting the desired polymorph on demand. We've validated it for cooling crystallization, but it would be really interesting to extend this to anti-solvent crystallization, both the models and the experiments, and that has not been done and will not be done in my lab. So what we've shown is that the design approach is feasible. That does not mean it's economical. And to understand whether or not it's economical requires a techno-economic analysis. That's another story for another day. So now let me tell you a little bit about continuous crystallizers and cascades of them. So the driver for continuous crystallization and continuous manufacturing in the pharmaceutical industry is the same driver that drives it in the chemical industry. Namely, it's easier to scale up, you don't have batch-to-batch variations, it's a safer method of manufacturing, and it frequently reduces costs. So all of these are the drivers. In continuous processing, one of the great achievements of chemical engineering is the invention of recycle. Seems like a simple idea, but it's actually quite profound in many respects. In some applications, it's absolutely vital. If you don't recycle or reflux liquid at the top of a distillation column back into the distillation column, the column simply will not operate correctly. But that's quite counterintuitive. you've already separated out the components at the top of the column, it's not exactly intuitive that you should put some of those as a recycle back into the column. So in some applications, recycle or reflux is absolutely vital. In other applications, it's beneficial and optimal, for example, in reaction systems. You might design a reactor to operate at, say, 40% conversion because of selectivity reasons, for instance. But if you recycle the unreacted reactants back to the reactor feed, you achieve 100% conversion over the entire process, even though the per pass conversion through the reactor might only be 40%. And so you might think this is a fairly straightforward application to pharmaceutical manufacturing. We'll design a crystallizer to have, say, 20% recovery or 30% recovery of the solute per pass of the crystallizer. From the outlet of the crystallizer, we'll separate the solids from the desupersaturated liquid. The liquid will recycle back to the feed of the crystallizer. And again, we would expect to achieve 100% recovery over the overall process, even though the per pass recovery might only be 30 or 40%. However, in pharmaceutical manufacturing, there is no recycle. That's a completely forbidden operation. It's forbidden in order to control impurities. It's forbidden for sterility reasons. And so this has a huge impact on process design. If you can't recycle, then you have to have a cascade of crystallizers in series in order to squeeze out as much solute as possible from the solution. Each of these crystallizers in series perhaps operates at a lower and lower and lower temperature in order to achieve that, or perhaps anti-solvent is added successively into each crystallizer in order to reduce the solubility and squeeze out more solute. So you can develop models for these cascades and find a number of interesting things about them. One of them, for instance, is the attainable region of particle sizes that you can get. So I'm plotting here the mean particle size emerging in the exit stream from the crystallizer cascade as a function of the total residence time in the crystallizer cascade for 2 crystallizers in series, 3, 4, 5, many. And what you find, let's focus on 3, because very often, as we know, 3 stirred tanks in series is almost always the optimal number. So let's focus on 3. If the total residence time is, say, 5 hours, then that cascade, on average, will give a mean particle size at most of 600 microns, and at the lower end, something like 200 microns. Turns out 600 microns is usually way too big, and 200 microns is also way too large. Typical crystal sizes in pharmaceutical manufacturing that are desired for tableting and formulation reasons are more like 40 to 50 microns. And so this opens the question, how do we reduce the size of the particles leaving the crystallizer to a range that is more desired? And I'll say a few words about that again in a minute. So this work was carried out by Thomas Farmer, who was a postdoc in my group, jointly advised by Chris Burcham at Eli Lilly. And Thomas published a series of papers in Chemical Engineering Science on this topic in 2014 and 2015. But meanwhile, chemical engineering practitioners are not standing by waiting for the phone to ring from chemical engineering scientists. They are moving on, developing processes as best they can. And I want to show one particular embodiment of a recent continuous process, pharmaceutical manufacturing process developed at Eli Lilly by Chris Burcham and Marty Johnson, and a large number of other people involved in it, of course. And they wrote about this process in a really beautiful recent paper published in this year, in 2021. And they give the entire flow sheet for the process. I've just cut out the section that deals with crystallization. And sure enough, they used a number of tools, simulation tools and other tools, as well as a great deal of clever experiments, to determine that 3 crystallizers in series was the optimal number. The solute, this compound, by the way, is actually shown in figure 3 in that paper. You can see what the molecular structure of the compound is. So this is not an unknown compound. This is something that we could, for instance, study in the university, in our laboratories. We could study in simulation studies and so forth. And what they found was that a good solvent to bring this compound into the crystallizer cascade was a mixture of tetrahydrofuran water. And then in the cascade, they dropped the temperature in successively in each of these crystallizers. So there's a temperature profile. And they added an antisolvent in each of these crystallizers to squeeze out more and more solute as the cascade goes along. The antisolvent was acetonitrile. And this paper gives an incredible, interesting collection of experimental challenges that they had to overcome and identifies a large number of really interesting research problems that we in the university should be conscious of and should start to investigate. So, the conclusion from all of this is that it's now possible to perform many aspects of digital drug product design and process design by both molecular and conventional simulation. We don't understand everything for sure, but it's becoming a reality. But as one of my former PhD students once told me, Wayne Fisher, who spent his career as a conceptual designer at Procter & Gamble, he once said to me, "Mike, the basic understanding of the physical mechanisms involved is always the barrier to good design. It's not lack of imagination." And so what are some of those bottlenecks? Let me mention a few of them here. The first, for molecular simulation, is better pair potentials, better atom-atom force fields, and better mixing rules for mixtures such as solute-solvent mixtures. This is still an area that's a real bottleneck in molecular simulation. I've not said anything particularly detailed today about nucleation, but let me mention that we really do need good models for heterogeneous nucleation and particularly for secondary nucleation. I can't emphasize enough how important it is to develop mechanistic models for these phenomena. Currently, the only way we can get our hands on nucleation rates is by experimentation. We need fundamental growth rate models at high levels of supersaturation. Fundamental mechanistic models are well known at low levels of supersaturation, but for antisolvent crystallization, high levels of supersaturation are what are encountered, and none of the existing mechanistic growth models apply at high levels of supersaturation. We should know more about impurities and their effect on crystal growth, which can be quite dramatic, and better models are needed for that. It would be excellent to have an attainable region study for crystal size performed, not just for the crystallizer as we did, but to have an inline wet mill in the process so that as the crystals are formed and growing in the crystallizer, they're put through a circuit with a wet mill that feeds them back into the crystallizer. And I believe that there is great opportunity for academic research studying this problem. And finally, let me mention, in chemical manufacturing, when we are concerned about impurities in the recycle, what do? We don't throw everything away that leaves the reactor. We recycle the unreacted reactants and put in a purge. Is it not possible in continuous pharmaceutical manufacturing to recycle the mother liquor from the last crystallizer and have a purge stream. So these are a collection of things that are on my mind for good research projects for the future. And finally, in the last few minutes, let me finish with some personal reflections on my PhD advisor, John Perkins. So here's a nice pair of photos of John receiving a medal from the Queen at Buckingham Palace. He certainly seems pleased. I was John's first PhD student, as measured or as dated the Cambridge way by date of matriculation, not date of graduation. So in my first year in residence in Cambridge, John's research group consisted of me. Here's a nice photograph I found in my files of John enjoying an after-dinner brandy in the hills of Slovenia at a conference we all attended in the late 1990s, and I was excited to see that in this image David Bogle, our chair today. So I particularly wanted to show this photograph of somewhat younger John Perkins and David Bogle enjoying some relaxation after a hard day's work. John was only in his early 20s when I was his student, but he was incredibly mature for his years. And there are 3 pieces of advice he gave me, which I am going to pass on to you. And I've used these pieces of advice on my own students throughout my entire career. The first is my favorite. I am your supervisor, not your foreman. Now, I've never actually said this to any of my students because I think they're all smart enough to deduce it from the way I treated them. But John was clearly taking no chances with me. Another important piece of advice is it's important to be given the freedom to fail. You learn a lot from failure, especially how to avoid it next time, and I think there's a great deal of truth in that. It really toughens you up, a little bit of failure. And the last quote was something he wrote at the end of a chapter in my thesis. I'd finished my thesis, I gave it to John to read, and I'd spent quite a bit of time as a PhD student getting into the intricacies of graph theory, and it didn't actually lead anywhere in my project, but nevertheless, I'd spent quite a bit of time on it, and I thought I ought to put a chapter in my thesis on the topic, and all John wrote on the beginning of this chapter is, just because you did it does not mean it belongs in your doctoral thesis. So I took it out. Let me add one of my own. If you want to have an impact, you have to write papers that change the way people think, like Peter Danckwerts did. So with that, I'd like to make a few acknowledgements. First, to my wife, Margaret Ricks. Here she is in Cambridge in 1976, enjoying a pint of Adnams ale, sitting on the banks of the River Cam, watching the May bumps. This is a more recent photograph of her. Our daughter Sarah and our son Max. My parents, Pat and Betty, and all my siblings. I'd like to acknowledge Mike Malone and Jim Douglas, who were great friends, and Mike still is, and collaborators for the first 25 years of my career, and I had a wonderful time collaborating with them back in the 70s, 80s, and 90s. I'd like to acknowledge Duncan and Suzanne Mellichamp, whose chair I hold in Santa Barbara. Of course, all my doctoral, postdoctoral, and master's students, too many to mention, but I would like to say, professionally, you've made my life really a joy. And also thank you to all the funding agencies who've trusted in us over the decades and sent us financial support without which none of these students would have been able to complete their research. And finally, thank you to you for listening to this. I'd be happy to answer any questions. Thank you for your attention.
Mike, thank you very much for an inspiring talk for your sort of journey, as it were, for over some years, I think, to really make a difference in this particular field in the practice and development of pharmaceutical products. And nice to see some of the bon mots. It's rather surprised to see my own photograph there, but I particularly like that one of freedom to fail. I think that's it's interesting that John was mentioning that all years ago, because it's something that scares graduate students to this day, and we really need to expose that we all fail and we learn from it, and not to be scared of it. So some questions. We have one question from Patricia Luis from the Université Catholique de Louvain. Thank you very much for the inspiring presentation. From your point of view, what is the potential of membrane crystallizations to substitute current crystallization processes in the industry?
I have to say, I'm not particularly familiar with the technology. If you're referring to using membranes in order to create supersaturation so that crystals stay on one side of the membrane and liquids on the other, I would imagine that's certainly a more passive way of increasing supersaturation, say, relative to evaporation methods. But I'm not entirely sure what aspect of membrane technology he's referring to.
Okay, she might come up with some specifics in the channel, but I had one. Actually, I was going to probe you a bit on recycle, but you've exposed a little bit at the end that that's current thinking, so I won't push you on that one. But because I think that has to change in some way, and accept that recycle needs to be part of this process. But I was going to have a broader question about the changes in the pharmaceutical industry in general, and us as chemical engineers, and the way, you know, they're talking so much more about personalized medicine, which will mean a very different scale of could mean a very different scale of producing things. It may be that they're all biologicals, but I suspect not necessarily. I wonder if you'd like to sort of comment on how that might influence us as chemical engineers, or do we just leave it entirely up to the bench scale chemists? But I have a feeling that's not really going to be very cost effective.
So I have a few things to say about that. I think that microfluidics and micro-manufacturing is the technology that makes this even conceivable. What I have in mind, for instance, are whereby you can monitor a person's blood sugar, glucose levels, and have it fed back to a little insulin pump with microprocessors that feeds the insulin in real time in a feedback fashion. And you can think of that, I'm sure, as one example of personalized medicine. And my former colleague, Frank Doyle, is very big into that technology, and it seems to work extremely well. They're not making the insulin, as far as I'm aware, on board. The insulin is loaded, and then it's merely distributed to the patient. I could certainly imagine in the future that microfluidics and laboratories on a chip and so forth could make very small amounts of certain kinds of products successfully. Of course, the place to begin is to start simple. Think of a medicine that is relatively easy to make as proof of concept. And we humans have shown over the course of history that if you start with something simple, like a microprocessor back in the 1950s, which might have been as big as this room, it wasn't exactly a microprocessor, that over time, humans are able to invent ever smaller technology, ever better technology, where now our cell phone has hundreds of times the microprocessor power of the Apollo space flights that took people to the moon. It just seems unimaginable, perhaps, that such progress is possible over just a few decades. But by analogy with those kinds of technological transformations, it's easy for me to imagine that say over the next 30 years or so that on-board personalized medicine, personalized distribution of medicine to your body in response to your own body's signals could become a reality.
Great. Thank you. That's very, very interesting. Just one more question. Actually, there's two, but I think we've only got time for one. Let me ask from Tabea Stadler from KIT, I think that's Karlsruhe Institute of Technology. Dear Professor Doherty, inspired by Professor Perkins' advice for advising students, do you personally have some advice for advised students? You've recycled.
What I actually do tell my students is you really ought to work on problems that people want to know the answers to. And it sounds simple to say that, but it's actually tricky. You have to really believe that what you're doing is important and that people want to know the answer. Sometimes they don't know they want to know the answer. And your job is to figure out the answer and then to make them want to know it. At the risk of sounding not very humble, let me use my own PhD dissertation as an example. John and I spent the years that I was in Cambridge developing residue curve map technology that basically didn't exist prior to my PhD. And then we published a lot of papers in the 80s and the 90s on that technology, extending it to all kinds of different situations. And at first, my research grants were turned down because nobody wants to know this. This is not conventional. This is not in the textbooks. This is not in the literature. But slowly, bit by bit, I had industrial sponsors. Jeff Sorolla, in particular, was amazingly good at sponsoring my work initially when other people didn't want to. And over time, we persuaded the profession that there was something to this technology. And now you can read about it in patents, you can read about it in papers, in textbooks. So I really believe you have to work on problems where you are convinced that the profession needs to know the answer. And sometimes the profession does know it needs to know the answer and is very receptive right from the beginning. But other times the profession has to be taught it needs to know this particular technology. And so perseverance and belief in yourself and in what you're doing, I think, is really important.
I think that's a really nice way to finish up. Problems that matter and make them realize that it matters, which is sometimes the journey. Thank you very much indeed. Again, Mike, it's a shame we can't meet in person, but I'm sure we will. I hope we will again before long, and we were not able to have you in Berlin, but I'm sure we'll see you then. If everybody can thank Mike very much, we can't really do applause, can we? So thank you very much indeed. And I will just say a few parting words to close the conference. Thanks very much.
Thank you. It's my pleasure.
So, there's a nice slide for sunset over University of California, Santa Barbara. We all wondered, we thought it was interesting that Mike would move from Massachusetts to Santa Barbara, but I think there is the answer. There should be a slide up now from my colleagues. It's my duty to close this conference, but before we close the conference, actually, I have a pleasant task to undertake, which is to announce the prizes for the poster competition. We had not sure how many posters there were, but there were a very significant number. I had a good look through them all myself. And we had some selection, and I can find for me somewhere I've got the awards. Oops. So the Third prize will go to, they've gone up on, no, they haven't gone up on the screen. The third prize goes to Katrine Rosenthal and Alexander Baer from the Technical University in Dortmund for their poster Biocatalytic Reaction and Process Development using a coiled flow inverter from reactor concept to ontology design. So congratulations to Katrine Rosenthal and Alexander Baer. The second prize goes to also to the Technical University of Dortmund, done well today, to Robin Dinter for a photoreactor concept developed by rapid prototyping for flow photochemistry. And that leaves then the first prize, which goes to Laura Marie Helekes from the Forschungszentrum in Jülich in Germany. Automated high throughput strain characterization from the frozen working cell bank to the final product assay. So congratulations to Laura Marie. And congratulations to all three. We had a clean sweep from Germany. I had a look through. There were a lot of really great work going on, and of course some really inspiring posters, really getting across their message. It was wonderful to see. So with that, I would also like to thank very much the chairs of the sessions. We had I think it was 14 parallel sessions. We had lots of chairs, many of whom agreed to do it at fairly short notice. So it's a great job that they all done. And of course, thanks to all the members of the program committee, all the reviewers, to the organizers, to the members of DECHEMA who've been behind the scenes steering the conference. And I'm sure I will have forgotten some others, but thank you all to everyone else, and of course thank you all very much to the audience, the participants today and throughout the whole conference. I think we've had a really great conference. It's difficult times still in the pandemic, but it's great to see that we were able to have this conference. And of course, we were to be in Berlin, and the EFC board decided when we go online that we should, instead of abandoning Berlin, Berlin will now be the next conference to be held in 2023. That will be in Berlin, in the City Cube in Berlin. So I encourage you all, would like to welcome you all there to Berlin in 2 years' time, and really encourage you to think about what you can contribute to, so that we have a really exciting program in this very dynamic city of Berlin, and hopefully we'll be all back together again and able to have a really big event there. So with that, I wish you all well, and we'll see you in 2023.